Thank you for having me. It's a pleasure to be here. I think my talk will be a little bit different from, let's say, most of the most of the other talks, as in it's more of a lesson learned topic more than a purely technical topic. So what I try to do here is to really, I mean, um, we built this company recently over the last few years, and we focused heavily on secure multi-party computation and machine learning. And I come from an academic background, and I think there were a lot of things that were definitely new to me, but also probably will be new to many in the audience here, and I just wanted to share. So without further ado, this is the agenda for my talk. So first I'm going to spend a few words on Keyless, what we do, who we are, and what we actually built. Let me see maybe if I can make this slides a little bigger. And then a few notes and a few lessons learned on how we've built and commercial MPC system, multi-party computation system, and then I'll touch upon a few challenges and insights that we had to face along the way. So the obligatory slide about the company. So we've been working for about 3 years, and we're about 45 people now, almost entirely engineers and researchers, and we're spread across multiple countries. So now we are in the UK, Italy, and Singapore. And what we're building, the product that we're shipping now is a multi-factor authentication system that allows users to authenticate with their biometrics, whether it's physical, like face, or behavioral, like for instance, movements and so forth. So with their biometric, but the key differentiator is that we use secure multi-party computation to perform biometric matching. So we don't do matching on the device itself, but rather we do matching in a set of servers that are able to compare encrypted biometrics with fresh biometric samples that are themselves also encrypted, provided during authentication. So this, as you can imagine, has a lot of advantages. For instance, I can enroll on my computer and I can authenticate on my phone. This is a pure software solution, so I can have the same biometric pipeline on multiple devices. And the templates are quote unquote transferred from one device to the other through secure multi-party computation. So there's no real transfer. The matching is really done in the cloud, but it's done securely. So Keyless or anyone who's running the servers that we have never sees any biometric data. But at the same time, we can get all the benefits of having, let's say, a centralized biometric repository. In addition to that, another thing that we think is super important that this technology actually enables is the ability to have, let's say, a fixed template. So I can enroll on a phone, and if I move to a different device or to a computer, the same, it's like there's a guarantee that the same template, biometric template, is used on both devices, because this template is stored encrypted in the network. And therefore, if I trust a certain user to have done, for instance, the KYC or know your customer step on one device, that transfer to any other device because the biometric is the same, which is not the case, for instance, with Face ID, where I could own 2 different phones with Face ID, and each phone could have a different biometric profile. So again, these are all benefits that you have with the centralized model. And at the same time, we address the drawbacks that are, well, but then you have to share your biometrics. We address that drawback with secure multi-party computation, which we think it's quite new and quite unique. This is because this is technical audience, I thought it would make sense to maybe spend a few words on exactly how this thing works before we go into how we got there. So the way in which this works is that during enrollment, we capture biometrics on the device. We do liveness detection, so we make sure that we're not looking at a picture or that there's no robot holding the phone. So we assess whether we're looking at or we are sampling from a live person or not. If we are, then we run a machine learning on the endpoint on the device to extract a compact representation of the user. We process this compact representation through a secure multi-party computation system that leads to having some data, some template that is stored then on the cloud, but the cloud cannot do anything with this template. It's a completely opaque cryptographic cloud. During authentication, we repeat a similar process, but in this case, this instance of the template processed through the secure multi-party computation protocol is then compared in the encrypted domain with what we have on the cloud. Based on the description I gave, some of you might be thinking, well, this is homomorphic encryption. Unfortunately, we can't do it. With homomorphic encryption, there are latency budget, there are security requirements in terms of adversary capabilities that homomorphic encryption, cannot satisfy at the same time. So we have some proprietary techniques that we had to design to achieve this. And as I'll discuss later in the talk, latency is really our low latency really is our main goal here, because when you're talking about authentication, really users don't want to wait, right? If they want to authenticate, it has to happen immediately within a couple hundred milliseconds at most. So, so some of the things I will say in the talk might not apply to a different use case where, for instance, you have multiple databases with terabytes of data that you want to compare privately, then maybe latency is not your main concern. But in this, and I would argue many other scenarios where you're going to use MPC in a commercial setting, latency is going to be one of the dominating factors, together with cost. And again, I'll touch upon that as well. But in a nutshell, this is what we do. So we use secure multi-party computation to compare encrypted biometrics. And we compare this in a distributed network. So there's another layer of complexity added there. We don't have a single region. In each region, we don't have a single node. Everything is spread across multiple secure multi-party computation servers, so that we have both redundancy but also resilience to certain kind of attacks that might compromise a subset of this node. So there's layer upon layer of complexity here, and this all affects both the design and the performance and the cost of the system. So this is the starting point, and this is what we tried to build and what we ended up building. So let's go all the way back to 3 years ago. So let's see where we started. So again, I come from academia, so in my head I had a reasonable design of how this could work. I had a couple of ideas. Me and my team, really, not just myself. We had a few good ideas. We thought at the time on how this would look like. We had some evidence that this could be done. We have some prototypes, something running in the lab that was saying, yeah, this does actually what you guys are claiming. And we managed to find a handful of good engineers and researchers that could actually support this effort. So, I mean, you look at this, so you imagine that you find yourself in this position. So you say, okay, I know what to build. I think I know what to build. I know how to build it. I have the people that can help me to build it. So how hard can it be, right? Well, I know everything I need to know. It's just a matter of execution. How hard can execution be at this point? I think I solve all the hard problems. It turns out, well, maybe not. Maybe not as much. So let's see what happened in over the past 3 years and what we've learned from this process. The first thing, I mean, it goes without saying, this is probably the most obvious one, but you have to be able to tackle from the ground up design complexity. Right, you know where you're gonna go, and if you're coming from academia, probably where you want to go is quite complex. There's a lot of moving parts, and you need to be able to get there. But at the same time, you have to start building something that is orders of magnitude smaller and simpler. Right? Yeah, I mean, you know that you're gonna build an aircraft carrier, but maybe the first version should be just a tiny boat, and this goes without. This I think is pretty straightforward. The main key here is not just pure complexity. That of course that's a good engineering principle, but the key point here is also change, right? You think you know where you're going to build on day one, but as you move forward, there will be tons of new constraints that will come up that will change that. And these constraints are not necessarily technical, right? Two of the most obvious ones are what the market will accept. Right? You're building something because you want to sell it. So that's an entirely new set of constraints that really will affect what you're building. And the second one, you need money to build it at the beginning. You're not going to start selling. You have nothing to sell yet. So you need investment, and you need a way, you need something to show that will convince people that, yeah, this is something that will eventually become this beautiful aircraft carrier. But right now I can see the path from this tiny boat to that giant thing. So this would significantly change where you're going. Let's say that you've been lucky, your team is very strong, so they're able to build something, some prototype, some large prototype, and if you're really lucky, maybe even SDK. Now what do you do with it, right? You need to be able to, that itself is not something, it's unlikely to be something that you can just package and sell. So you have this thing that is wonderful. You've proven your point, but I don't know how much you have to show. You really have to target at this point a specific audience, right? You need to be able to choose very carefully who you're building for. And at the beginning, it might not be for customers. It might be for investors, so that later on you can build for customers. So what you really should think about is more about the system, this minimum viable system that can come out from these foundations, right? Now you have these foundations, you need to add a lot of pieces around it, and or you're gonna find yourself is in that, well, the hard part, let's say the fundamentally new research part, the fundamentally new technology or scientific part, that is code-wise maybe the minority of your code base, right? That might be 10, 20% of your code base. And you're going to see that a lot of the time, a lot of the resources of your team are going to be spent on the plumbing and really the what's around your core technology. Maybe something that many can relate to here, like if you're building some privacy preserving database system, for instance. Yeah, there's a lot of thought and a lot of technology that goes into the MPC to do that. But at the end of the day, you're still building a database. You're still building an API that developers can use to interact with the database. You still need to build a distributed system, servers and client talking to each other. So ultimately, from the ground up, you need to plan for non-crypto code, non-MPC code to be really the vast majority of the code that you're going to write, and therefore the problems that you're going to have. And this gets me to the next point. That is one of the insights is that we had is that you have to be able to build something that is a core that is robust and not only robust but also flexible. So for instance, you have this beautiful MPC protocol that maybe outputs 1 bit. For us, for authentication, will be yes, this is the user, no, this is not the user. But maybe you look at it and you're saying, well, for a little bit extra effort, I can output, instead of 1 bit, I can output maybe more than that. I can have a slightly more complex functionality that today I don't really see the use, but I can see, but maybe in 6 months there will be. And it turns out that more often than not, I don't know, 3, 4, 6 months later, there will be a beautiful use case that you haven't thought about, that someone brought up, an investor, a customer, and because you spend that little extra effort, you made it a little bit more versatile at the beginning, you can immediately copy, right? There's very little extra work you have to put at that point. So the insight here is build something robust, build something flexible. It won't be immediately clear why you need all this, but at the same time, if a little extra effort gets you a slightly more general piece, there's definitely value there that in building and investing the extra time, which is in a way to say plan for change, right? The more flexible you can be at the beginning, the more you can be flexible later on with change and not having to update what your technology does, which is going to be the hard part. And I talked about latency earlier, and I just wanted to touch upon again here. Again, in our system, but you will see many MPC systems that you want to ship commercially, latency is definitely going to be a factor. So definitely you need to have a core, a multi-party computation protocol that allows for low latency. For instance, I mean, you want to have one of these protocols to have a very small number of rounds. Rounds are expensive, so you want to minimize that. You want to have a protocol where you can have very low computation overhead so that you don't spend a lot of time waiting for the other party to do its part. But you will see that that is not enough. This piggybacks on what I was saying earlier about even just a proportion of code that is MPC and that is not. And you'll see that maybe a lot of the time will be done on serialization and deserialization of the data that you have to send back and forth because of some of the choices you had on the protocols that you want to use, right? To exchange this data between the two parties, and so on and so forth. Maybe the infrastructure that you're setting up for the load balancer is a bad match for your MPC protocol, and you will have to adjust that. So the point here is that while having a core technology that allows for low latency, it doesn't necessarily mean that this will translate into that. So that's another thing to take, I think, into consideration when building. And one final point here is about bottlenecks and cost, right? So it's going to be very hard at the beginning to understand where your main bottlenecks are and what is going to be the most expensive part of your system. Because at the end of the day, if you're building a company, it has to be profitable, and if your system is beautiful but way too expensive to run, that's just not gonna work. It's just not gonna cut it. So you might be surprised, hopefully not, but you might be surprised about where the cost goes, right? Depending on who you ask, they will tell you, well, computation is going to be the most expensive part in your secure multi-party computation system, or communication will be. But then you start digging, and maybe storage, right? Storage in the cloud is not that expensive, but if you're doing MPC, it's easy to store, to end up coming out with a protocol that stores gigabytes of data for each user, right? And hopefully you're not in that position, because not only that will make it extremely expensive, but also you'll find yourself stuck, unable to work on certain infrastructure. For instance, one of these newer edge computing infrastructure where storage really comes as a premium. So again, the obvious places where the cost might not be in the obvious places, and it might be in something that typically it's safe to overlook in an academic paper, but not really once you then go to production, right? And it could be something even more transient, as how much memory is needed to run the protocol. It's all transient, but well, you still need to provision for that. So, or that significantly affects your scalability. So these are all things definitely to consider. Again, protocol itself is required to achieve low cost on all these items, but it's not necessarily sufficient, and it's not necessarily clear at the beginning where you're going to hit a bottleneck. And just to broaden things a little, another thing that you're probably going to hit is client platform integrity. You are still running on client platforms that you don't control most of the time. So integrity there is going to be a remarkable change. You cannot expect that you will have integrity, even though there are trusted execution environment and secure enclaves. None of that will really save you in practice. And you really have to design from the beginning to run on an untrusted environment as much as possible, which will shift the burden of the computation a lot from the user's device to the cloud on as many things as possible. And that will imply more constraints on the privacy side. Okay. I'm running a little bit short on time, so it's probably better if I stop here and maybe we open the floor for question if there's any. But before I do that, let me thank everybody for attending and for listening.